It's Mr. Gustin. I'm back in the physics classroom, and today I'm going to show you two demonstrations. I'm going to show you two things that probably aren't new to you, but two things that we can now start to explain using our understanding of physics. And that's kind of the goal of this whole thing, right? Is to see things that are not necessarily unfamiliar, but then try to explain things that we haven't been able to explain in the past. So I've got this over here. We've seen this before, I think. It's called the gyroscope. It's a bike tire on a pretty frictionless ball bearing system right here. But we're going to see what happens with it, okay? So it's no doubt there's a handle. Here's how it works, I guess. There's a handle on the side, and it goes through. And you can see that if I rotate one side, it also spins over here. Like it spins on both sides, so it's a through axle. And then there's a bike tire up here. And this bike tire isn't really a tire at all. It's filled with something, so it's not. There's no air in it. It's just kind of solid rubber. All right, but I'm going to get this thing spinning, and we will see what happens. I'm going to get this thing really cranked up, spinning really good as best I can, moving it very quickly, angularly, so we have a high angular velocity, and then I'm going to set it on the ground. And once I set it on the ground, what you see is that it continues to rotate. It doesn't touch the ground. It's wobbling a little bit, but for the most part, it's staying up until the air in the room and any friction that exists in the ball bearings takes over. But even look at that, it's not touching the ground still. It's pretty cool. And now it slows to a stop. Let's see it again. This hurts my hand, but I'm doing it for science and for you. As long as I get it set up the right way, we see it kind of sitting right here. And we notice that it's rotating in the clockwise direction. It's rotating clockwise. And so because it's rotating clockwise, or counterclockwise, I suppose, I guess it doesn't matter, we notice that it stays up, which is weird. So it finally, I can hear it. Now it's going to come to a stop when it hits the ground. Let's go ahead and draw ourselves a little model. Here is our bike tire. It's spinning. Here's its through axle. This looks this looks like a top. Like I think we've seen this before. If you've played with like Beyblades or tops or things like that, we've definitely seen this before. And we're going to say it was moving in this direction. That was its angular velocity. It was here. We'll call this spinning tire. And it stayed up. It didn't fall, right? There was obviously gravity acting on it, pulling it down, but it didn't wobble. It didn't stop. It stayed put. And that's curious. That's interesting that this thing didn't stay put. And so if we think about why that is, we think about the first law, or Newton's first law, which is objects in motion stay in motion, objects at rest stay at rest. What Newton is really talking about in this law is the momentum of an object. If an object has momentum, whatever that momentum is, it's going to want to maintain that. If its momentum is zero, it's going to require an outside force to change its momentum. If its momentum is something else, it's going to require an outside force to slow it down or speed it up. This is the first law. And so we have to talk about angular momentum in this case. So angular momentum is the object's ability to move or not move in a certain way. It's very closely related to speed, and it's very closely related to rotational inertia. If we think about what linear momentum was, this was mass and velocity. So as we think about angular momentum, we think about what variables might replace linear momentum. And so we know that, well, let's start with L. L is angular momentum. It's the variable we use. Instead of velocity, we use omega. And instead of mass, all unit long, we've been discussing mass is rotational inertia. It's the shape and size of an object that dictates its inertia instead of just mass alone. So this equation here is my angular momentum expression. The question is, how does momentum play a role here? Like, if I understand that if this object is moving forward, the momentum of the object is also forward. But that doesn't really help me understand this momentum here. Right? If I'm rotating clockwise, the momentum is clockwise, and if the momentum is clockwise, this thing doesn't want to rotate outside. Like, it's a weird thing to say momentum is clockwise. So we have to think about the direction of momentum. And what I want to teach you now is called the right hand rule. So everyone take your right hand, you're going to put that up, and you're going to move your fingers in the same direction that this object is rotating in. So for us, this object was rotating clockwise. So get your right fingers to make a clockwise circle. And so I have to flip my hand over, face my palm away from me, and curl my fingers. This is my clockwise finger curl, okay? It's going clockwise. The thumb, my thumb, if my thumb is in anatomical position, which is just like high five position, fingers curl, thumb points down. The thumb in this right hand rule indicates to us the direction of angular momentum. Angular momentum is exactly perpendicular to the rotational plane. So if this thing rotates in this plane, the momentum operates here. This is the direction of angular momentum. It's up and down. It's into and out of the page. So why does this object stay up? The object stays up because angular momentum is vertical. Therefore, the object stays upright until an outside force changes the direction of momentum. That would mean I would need some kind of force to push this thing over, rotate it downward, twist it downward. Or I simply need the tire to stop rotating, to lose its angular velocity, and then its angular momentum gets closer and closer to zero and wobbles over to a stop. If there's no momentum, it's pretty easy to kind of change that object's momentum. If it's not rotating in any specific way, it falls over pretty easily due to the force of gravity and the unbalanced nature of the object. But this is it, right? This is Newton's first law. Here is the momentum. It is vertical when I rotate the tire. Therefore, as it continues to move this way, the tire will remain upright unless it comes to a stop or an outside force acts on it. This is a pretty cool thing, I think, for us to understand and for us to look at. Okay, this is an example of angular momentum alone. This is what angular momentum is. It's what it does. On the flip side, though, we have a different kind of idea. We have this is just momentum of the object, but just like we had momentum and angular momentum, now we also have conservation of momentum. Okay, so we're going to look at not just the spinning tire. Now we're going to look at the spinning chair. And a spinning chair demo is a demo we've done many times in many different ways, but essentially here it is. I have got a chair over here. Actually, I'm going to move the chair over in this direction. Maybe we can see this better over here. I've got a chair over here on the floor. If you're in my classroom, this chair is something I use quite regularly just to sit on because it's a nice little short stool to sit on. Couple things. This chair is relatively frictionless, and if I get on it without moving, I'll stay put, other than the non-level nature of my floor. But I'm not going to move a whole lot here on this chair because I did not have an outside torque on me. So if I start to try to twist myself around with these masses on me, what you'll notice is that as I move my arms in one direction, my knees go the other direction. That's because I am rotating one way, and so my knees, to conserve momentum, rotate the opposite way. This is exactly an example of conservation of angular momentum. I twist one way, and the upper half, the lower half goes the opposite way. And this is so that, or because, there is no outside torque changing my momentum, so I can't just create motion out of nowhere. Now this is obviously a pretty simple example. On this chair, I could probably actually start to get myself to rotate. If I start moving my arms out and then back in, I can actually start to see myself start to rotate around in a circle because I'm taking advantage of some friction forces and some weird momentum things. What I really want to show you, though, is not from rest. I want to show you what it looks like when I start from moving. So I've got these two masses in my hand, and I'm going to start rotating myself with these masses out wide. Like my arms are out with these giant, these are 2 kilogram masses in each hand. So my arms are out wide, and then I'm going to pull these masses in, and we'll see what happens to my velocity. So I'll start with my arms out here. I'm going to start with my arms out, 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 out. And then as I go ahead and pull them in to my chest, you can see that I start to spin faster and faster and faster. Then I'll slow myself down again by pulling them out, or pushing them out. And then I pull them in again, and I go ahead and speed up. So spinning chair demo. I'm a little dizzy. That was, woo, dizzy. Spinning chair demo. 2 things. I'm sitting on the chair. There's me sitting. I'm not the artist. And I'm rotating with an okay angular velocity. But then I go ahead and I pull my arms in tighter. And when I pull my arms in tighter, I get a much larger angular velocity. There's a change here. The question is there an outside torque? And that's my first question, right? The first question I have to ask myself is there a torque? And by torque, I mean like an outside torque. Why? Because if there was, then there's a change in angular momentum. And if no, oh, sorry, that's one. And then if no, then there's not a change. And so I will ask you at home, was there an outside torque on me? Obviously, yes, I started myself moving, but once I was moving, was there an outside torque? I mean, I pulled the objects in, but that was me applying a force on the masses. That's not necessarily an outside force. I mean, was there friction? Maybe a little. Was there gravity? Yes, but that's not going to cause me to speed up or slow down rotationally. So as I think about this, there are not any large, non-negligible outside torques on me. So what this means is that angular momentum was conserved. Just like we had in unit 5, if there's no outside force, momentum is conserved. Well, now if there's no outside torque, angular momentum is conserved. And so we can say this. We can say that the initial momentum that I had is equal to the final momentum that I had, which means the initial I times omega initial is equal to I final times omega final. What did you notice? We noticed that as I moved from initial to final, my speed increased. The speed that I was moving at increased greatly. I felt it. I'm still dizzy from it. If there's no outside torque, this is where I get kind of confused, right? If there's no outside torque and my speed increases, that must mean my rotational inertia decreased. Something about my rotational inertia decreases. So let's take a closer look at what rotational inertia is. This is my mass times r squared with some coefficient out front. What changed? Did my mass change when I pulled my arms in? Certainly not. I change the radius. I change the distribution of mass. And so by doing this, by pulling my arms in, I actually, in real time, am changing my rotational inertia. In order for momentum to conserve and remain conserved like we know it does, this means I'm going to move faster because my rotational inertia decreases. And this should make sense. I am moving with some speed because I have some inertia. Inertia is the resistance to changes in motion. But then I quickly change my rotational inertia by decreasing it. I'm going to move much faster. I'm an object with less inertia experiencing this same type of motion. I'm going to move faster, and that's what I see. And then when I push my arms back out, I notice there's a decrease in angular velocity because of the increase in rotational inertia. And this interplay back and forth shows up in diving, in gymnastics, in dance, in a lot of different cases where I'm seeing objects that are wide and then small and small and then wide. We see this kind of conservation of angular momentum, and this is the explanation for why this is the case. This is some explanations around it, around what angular momentum is, and around what conservation of angular momentum is. There are parallels between linear motion and angular motion, and I hope you're finding them. Okay? If you've got questions on either of these demos, drop them in the comments, send me an email, or as always, ask me in class. Until next time, see ya!